at this microphone.
Oh, should I just stick it here?
Yes, yes.
How do I change a slide when I just want to move one?
Oh, yeah. There's a clicker here. So the shape.
Fascinating.
There. So you can.
Forward, backwards.
Yeah.
Okay, I could just leave this here and okay.
Yeah.
Okay, great, thanks.
So, so let's start the afternoon session. The first speaker of the afternoon session is Leila Schneps from Paris. So, please.
Thank you. So first, normally I would thank the organizers, but I am an organizer. So in this particular case, I thank Mohammed, who had the idea and invited me to join him in organizing this conferences. I love conferences where there are a few people all on close subjects. So my talk is going to be in many ways related to the talk we just heard by Ulf, but GT is hiding in it. GT is like a spider in the center of a web that radiates out in many surprising different directions. So it may sound like the subjects can be quite different, but GT is somehow at the heart. And when the time comes in this talk, I will explain where GT is situated and why my talk is relevant to GT. The GT that I will use in this talk that I will even mention in this talk is uniquely the Lie algebra version of GT. So that will come later. What I'm going to do is I'm going to tell you why I'm giving this talk, what I'm doing in the talk, and I'll give you a little plan. So I'm going to talk about multizeta values, the ordinary kind, but with many things that we just saw in the context of Q multizeta values in common, which I will briefly recall some and then explore others. The motivation for my talk is the same as Ulf's motivation, namely, I was asked by physicists who are working on scattering amplitudes to please, if I could answer certain questions with my knowledge of the mold theory and then multiple zeta values. And I said, well, yeah, sure, there's an easy explanation for that. And then they were very excited and told me that, so I'm going to give a result which is simple and which I knew for a long time. But the result I'm going to give is canonical generators for the motivic multizeta Lie algebra. A very, very simple way to choose canonical generators. And it turned out, which I hadn't really paid attention to all this time, that many people were asking this question in many lectures and many papers and saying, we don't have canonical generators for this Lie algebra. It's a free Lie algebra. This is Francis Brown's wonderful theorem, which I'll recall in some more detail, including with generators of the Hopf algebra of multizeta values and the Hopf algebra co-module. I will recall these structures. But in any case, he proved this wonderful theorem that on the level of the Lie algebra, it's free with one generator on each odd rank, which are closely related to the absolute Galois group as the Soulé characters. I will very briefly recall this at the beginning because this is not something I'm going to use. It's just sort of context. But the thing is, because you have these free generators and you can bracket them together in a given way, we're not sure which is a good generator to choose. There's no good choice. So what I'm going to do is I'm going to use duality between multizeta values and their duals to give a very, very simple method to make a really clear canonical choice. Okay, so I'll do this. One is just going to be a little background situating an introduction and recalling background. Is this too small or is this okay? Then in two, I would really like to discuss the whole issue of duality. So everybody has seen the double shuffle Lie algebra, the Lie algebra that Ulf was talking about, and people have all seen multiple zeta values, and we all know there's a duality. So I'm going to make a very, very beautiful, clear structure of all the dualities on all the levels. And then the third part will be to just use this duality in a simple way to get canonical, two canonical things. One is canonical decompositions of MZV algebra into pieces of certain type, reducible, irreducible, single, so forth. And from this, related to the same, I mean the same argument, canonical generators for motivic MZV Lie algebra. So that's the plan, and it's not difficult. It's all very, very basic stuff that fits nicely together, but it seems to answer a question that was asked by many people, and in particular, this was asked to me directly by these physicists who are working on these things, which, like Ulf, I have no idea what they're doing. Okay, so I'll just erase this and just recall background. So in recalling the background, I'm going to, this is the only time where I'll situate where the Galois group GQ and GT fit into this talk, just so that we understand the relations. And after that, it will just be the multizetas. So the absolute Galois group acts on the pi1 of the sphere minus 3 points, which is just free group on 2 generators, pro-finite completion. We've all seen this before. We all know it by heart. And I'm going to write it this way. But what you can do is you can quotient this group by any characteristic subgroup, and you'll still get an action. So you quotient it by the subgroups of the lower central series. And you write Galois Q n equals the kernel. So now what you have is you have a filtration of Galois Q by this. And you take the successive quotients. So the bigger n is, the smaller the kernel, because it gets finer and finer. So
What do you mean by the injective? Is this injective?
no, of course not. Sorry. It was injective before I bought it out. Yeah, it was injective. It is no longer injective. So you take just the successive quotients of these subgroups, and they're all abelian. Add them all up into one big thing. And you get here a vector space. But you can make this into a Lie algebra in a very natural way, where the bracket really comes directly from just commutators of Galois elements. It's called the Deligne Ihara Lie algebra. And you can even define this over Z, but yes, you can tensor with Q and have a Lie algebra over Q. So this, thanks again to Brown's theorem, which is a powerful theorem that can be restated in many equivalent ways. So a consequence of Brown's theorem is that this Lie algebra, I believe it was Hein and Matsumoto who proved that this Lie algebra has one generator in each odd rank greater than or equal to 3. So it's generated by elements sigma 3, sigma 5, and so forth. And a consequence of Brown's theorem is that these are free generators. So remember the structure, just a free Lie algebra on some symbols, sigma 3, sigma 5, sigma 7, which have weights. If you can make it a free Lie algebra graded by weight, where each of these symbols has the weight of its index. That's the structure of this. Then you have a second Lie algebra, which is the motivic multizeta Lie algebra, which I will then erase the board and define in a minute. But before I do that, in between them, there is, of course, the Grothendieck-Teichmüller Lie algebra. So this is inside the Grothendieck-Teichmüller Lie algebra, which is the Lie algebra associated to the Grothendieck-Teichmüller group, GRT. The R is there not for Grothendieck, but because it's a graded Lie algebra.
What is the gamma?
Sorry?
Is there a gamma? Right above the GRT?
That's a sigma, sorry. Yes, I'm not an expert at my Greek writing. So these are symbols for the free generators. Later I'll be using G's for other. Usually people use F for this one, G's for multizetas, but it's always the same idea. Here's the thing. Because GQ is into group GT, which we've been seeing, and maybe equal. This is in there, and it's not difficult to go from GQ and GT to this inclusion. However, it's an inclusion, right? We don't know GQ is GT. We don't know that GRT is free with one generator on each odd rank. But what we do know now, thanks to Francis, is that there are such elements in there which maybe generate the whole thing, and which in any case are canonical important Galois elements that are inside it. So the result here that I'm going to explain today does have a consequence on the Grothendieck-Teichmüller-Lie algebra also, in that it gives a family of canonical elements which are potential generators. Okay? And now
sorry, it is implicit, but to get that, say, the linear algebra, do you fix some prime number L?
Oh, yes, you're right. You should. Okay, so let me say one sentence about that. You should fix a prime number L, and this should be really defined over QL. In fact, they don't have any direct definition over Q or Z, but now we do. Why? Because here, okay, you ought to do this. But here, you can also include it into, and now this is again the theorem of Francis Brown, the motivic multizeta Lie algebra. Motivic multizetas, they are going to form a Lie coalgebra, and this I'm going to explain it carefully on the next board. The dual is a Lie algebra, and this Lie algebra contains this naturally. And this, he proved, is free with one generator in each odd rank. So we know now that, in fact, this map is an isomorphism. It used to be contained in, but now it's like this. But this one is defined over Q, and therefore now we know that essentially there's a motivic version of this defined over Q, such that when you tensor it with QL, you get all the L versions that were originally. And that's actually rather interesting. It's true that I should not have written profinite here. I should have written the pro-L completion. It doesn't seem to be possible to do this directly, and yet, once you know this theorem, I tend to forget that, because this theorem says, yes, there is a version over Q, and all you have to do is tensor it with QL to get the other versions. It's truly a motivic version in the original sense of Grothendieck, which says we have something over Q, even over Z, and we tensor it with QL to get all the L versions of the family of all the L versions. Now, GRT is inside, and this is also inside the double shuffle Lie algebra, which it is part of the multizeta theory that I'm about to define more completely. This part here is finished. This is really just the introduction, recalling how would I'm going to be, why I'm talking about multizetas, why they're related to Galois and GT, and kind of the framework that contains the question I'm asking. The question is, knowing that this is generated by such elements, is there a canonical choice? And the very first non-canonical thing that people look at is in weight 11, because there's a Lie bracket on here, which I'll talk about, which is just very related to what Ulf was saying. There's a Lie bracket, and so you can bracket these together, and you have F11 in weight 11, but you also have F3, F5, which is also of weight 11. And so you don't know, a priori, people say, well, I don't know which one is canonical, I don't know which one to pick. So this is exactly the thing which I'm going to just give a very, very simple reasoning to pick. This, and also not only for odd weights, but also for even weights, I'll give something which I will explain why, starting now. So now you can forget everything to do with everything except multizeta values. We're going to just stay with those from now on. So I'm going to start with this algebra, just the algebra of polynomials in X and Y, non-commutative variables. And I'm going to consider it just as a vector space for a minute, just as a vector space. And this is its vector space dual. I'm going to use dual. I'm going to use just a symbol Z, which is like a kind of a lifted zeta of W for W all monomials in X and Y. monomial. So what am I doing here? Just here I take all monomials as a vector space basis. Here I just take the dual basis. And the action is just z of w on some other monomial v is just delta wv. So if it's z of that monomial, it's 1. If it's not that right monomial, it's 0. Okay, now what I'm going to do is I'm going to take a quotient of this algebra. And it's going to go to formal multiple zeta values. So again, Ulf quickly reminded us of the shuffle relation, the Stuffle relation, regularization, the coproduct, things like that, which I'm just going to write down explicitly here in a couple of lines. Without full definitions, partly because he gave and partly because everybody knows them already. So, okay. Remember that the multiple zeta values, these are the real ones. So below quotient down here, we're going to have motivic ones, and below motivic ones, we'll have real. And I'm going to discuss all the levels of this diagram. So here I'm going to just define the real ones, recall the definition, which everybody remembers very well. So these are the real multi-zeta values. They converge when k1 is greater than or equal to 2. And we have a very, very simple translation to connect them to words w in x and y, which goes like this. We write zeta k1 kr is equal to zeta of the word x to the k1 minus 1y, x to the kr minus 1y. So this is just a coding differently, okay? And now, using a formula which I saw many decades ago in an article by Hidekazu, we define zeta on every word. So every word looks, this word starts with x, because remember here we have k1 greater than or equal to 2. This is only for the convergent case. So this word starts with x and ends with y. But what if we have a word that looks like this, where v is a convergent word, but we have some problems there? We just shuffle it all in. So we're going to take r from 0 to a, s from 0 to b. There's a sign, r plus s. We peel out some of the y's. We peel out some of the x's, and we shuffle in the rest of the x's. So this is a definition. This is a definition. It's a very interesting definition in several ways. Firstly, it looks like it still contains a whole bunch of zetas with non-convergent words, but when you do actually develop it out, they all cancel. And you don't even have to like do mod anything. They actually cancel and go away. And you end up with a linear combination of only convergent words. That's one thing. And the second important thing is that if you take these values, of zeta w for all words w, convergent, these real numbers, and non-convergent by the formula, you have this wonderful formula that's always true. So the shuffle of two words in x and y is the shuffle that Ulf defined before, where you really just take the letters of one word, the letters of the other word, and you mix them all up. You permute them in every possible way such that the order of each of those words stays, but they're all mixed up and braided, shuffled into each other. Shuffle is this English word that doesn't exist in French, where you take a deck of cards, divide it in two, and then you go brrr, like poker players, and each half stays in the same order. I saw a wonderful, wonderful, amazing magic trick once by Percy Diaconis, who's famous for his magic tricks, but where he actually took a pack and shuffled it 3 times, and then he was able to, and then someone chose a random card and put it back, and then he was able to find that card. Because he explained to us that shuffling 3 times doesn't mix them very much. He showed how to read the order. It was very interesting. Okay, you can't say shuffle in French, it doesn't exist. So they say mélange, which means mix, which is a terrible word. French is a terrible language. The French say preuve when they mean evidence, doesn't prove anything. Like when you're in a trial, which I often am. La preuve, it's not a proof. Okay, so fortunately I speak English, so I can say shuffle, and also I shouldn't digress with funny remarks. But anyway, you have this, which is this Okay, beautiful identity. And these are called these are thus actual convergent real values because they're all just linear combinations of real numbers. And they're called the shuffle regularization values. Sometimes people write a little shuffle here. I don't bother. To me, these are the true zetas. Okay, next you have this other multiplication called stuffle. Once again, I'm sure you all know perfectly well, so I'm just going to remind really quickly what happens if I multiply zeta 2 times zeta 2. You multiply the two series, you just multiply these two series, and then you break it up into n greater than m greater than n, and m equals n. So this one is 1 over n to the 4th. And here you have n squared, m squared. So what is this really? It's just zeta 2, 2. And this is again zeta 2, 2. And this is zeta 4. So zeta 2 squared is also equal to this. And that is a different multiplication that you get what you get here. So it's the other multiplication rule called stuffle, which Ulf was also talking about. And I'm going to very quickly in one line just remind you, there's also a stuffle regularization. So you define this on convergent words, in fact, all words, if W ends in Y. And then there's a formula if W is convergent, I should say, starts in X and ends in Y. There's a formula for zeta of 1, 1, just the ones, which is quite simply zeta of 1, 1 is the same as y to the n. Take the sequence, expand it out, and you get these numbers, all of these. And then there's a general formula for y to the j of v, where v is a convergent word, which is very similar to this one. You peel out some of the y's one at a time. And you do this inductively by first with just 1 y, 2 y's, and so forth. Okay, so this gives you a bunch of zeta stars for all words ending in y, and they satisfy the same relation. But here, the product of these words is different. It's the stuffle product between words, which we also saw earlier in Stock. Okay, so you have two different sets of zetas. Now, what I'm going to do is I'm going to go over back to this diagram, and I'm going to say, I'm not going to make, it's going to happen by itself. I'm going to make this, I'm going to consider this as an algebra now. In fact, I'm going to consider it as a Hopf algebra. So the coproduct is just going to be x tensor 1 plus 1 tensor x, and the same for y. And the multiplication is just concatenation. And over here, I'm going to, by duality, this one will become a Hopf algebra also. And the multiplication is the shuffle. Okay, so this quotient here, when we say formal multizetas, what do we mean? Formal multizetas are just values that look just like this, but we write a little f, so they're not real numbers, they're just symbols indexed by these, and they satisfied all of these relations with this definition and all of these relations, and nothing more. So of course, this is a huge conjecture concerning real multizeta values, which we don't even know if they're rational or multiples of pi. We don't know anything. We don't have any transcendence information on them. But for the formal multizeta values, the definition is we just have shuffle and stuffle, regularized, and nothing else. So I don't have to mod out by the shuffle relations. That is the multiplication on my algebra. This relation here is equivalent to making my vector space into an algebra. But I do have to mod out by the stuffle relations. So modding out by stuffle multiplication. That's the kernel of this map. And over here, I'm going to write dual. It's the wrong, I'm going to write dual on this side, let's say. I'll leave MZ on that side, and I'll write dual on this side. Okay, so So this is inside, because whenever you have a quotient of one space, the dual is automatically a subspace of the other space that annihilates the kernel. Okay, now, before I go to the next step, which is going to be multizeta values motivic, MN? Oh, I'm just going to write MZ. I'm just going to write MZ. It's motivic zetas. And then I'll just write Z for the real ones. Okay, so before I go down, I need to talk for a minute about what Ulf already talked about, which is the Goncharov coproduct, the Goncharov-Brown coaction. So I don't know about you, but personally, I hate the word Hopf algebra co-module. I would rather see what happens in the dual. And all that thing means is that on this side, it's a module over a Hopf algebra module. And I want to show exactly the structure of that. So first, let me remind you that, so I'm going to do this. FMZ mod the formal zeta of 2, the ideal generated by that. Here we'll get MZ mod the motivic zeta of 2. And here, just Z mod zeta of 2. This is an algebra, since if we multiply two zetas, we get a sum. We just saw that with the shuffle. So it's certainly a Q algebra, so I can mod by the ideal. Now, what Goncharov did is he showed that this space, which I'll just call FMZ bar, this space is a Hopf algebra, and he put the coproduct on it. And over here, we have a dual, FMZ bar, and I shouldn't have an arrow, because these are all contained in each other. MZ bar, Z bar, bar, MZ dual, Z dual. I think I have a slide of that, so in a minute I'll just put up the slide. It's big and complicated. But I want to talk about this. First, this. It was made into a Hopf algebra by Goncharov, and then Brown showed that while you can't make this one into a Hopf algebra, it's close because there's a coaction.
Maybe you skipped in the line, because for the motivic Goncharov was in the motivic portion, it was proving the coproduct, and then for the motivic, he extended. So they never talked about formal ones in Brown and Goncharov. They only work on the motivic.
I'm not sure that's true of Goncharov. At least orally, he certainly spoke about the formal ones. It's possible that the coproduct is exactly the same and it works for both. But I'm not sure that Goncharov did not ever put his coproduct on formal multizeta values. In any case, the same product. It's the same coproduct for both. And maybe now is the right time to show a couple of slides, because maybe you're familiar with this coproduct already, and I don't need to. How did he do it before? Oh, okay. Before let me just very quickly recall Goncharov-Brown coproduct and coaction. So that's just another coding. When you have K1, KR, you can put it as a word in X's and Y's like I did before, and then you put the word backwards and you change the Y's to ones and the X's to zeros. This is the same coding, really. And then you have some rules here concerning these motivic multizeta values. The I's are what they call motivic multizeta values. And the coproduct is here. You write all your letters around a half circle. You take all the polygons starting at the endpoints, but inside your half circle. Here on the left, you put one term that corresponds to the chosen polygon, and on the right, the product of all terms corresponding to the pieces that are left out of your polygon. And many of those pieces go away because of these because of these different rules. For instance, if you have only zeros in the middle, it goes away, or only ones, and many of them drop out, and then some of them stay, and that's how you calculate your coproduct. So here's a little example where there I just took one term, but if you want to calculate the entire coproduct, you have to take the full polygon with everything in the trivial polygon, and then all of the inner polygons, but most of them go away. The only ones that stay are the ones that's shown, and then the one that goes to this one and that 0, and the one that goes to this one and that 0. Only 3 of them stay. Whoops. So you get a 3 here. Okay. So the coaction was extended from mod zeta 2 up to including zeta 2 by Francis, who simply established that if you define it on zeta 2 tensor 1, it works. So what does this mean? What does this mean? Now, okay, let me put that complicated diagram back now. Okay, so here's our whole diagram of everything that I just said. I can erase it now because it's better here. All the objects I'm talking about are shown. So in this diagram, all these spaces here, all of the ones that are with little duals on them, all of them are subspaces of polynomials. And all the spaces that are surjected down by the space of symbols are all different multizeta spaces. So here, these are algebras. They're all algebras. This is the Hopf algebra comodule. This one is Hopf algebra. This one is when you go mod products, Hopf algebra mod products. That's just a Lie coalgebra, in fact. And this is a Lie algebra because it's a dual. So here's the formal ones, starting with, we know exactly what relations are satisfied by our formal multizetas. Here are the motivic ones, which I'm going to tell you about them in a second, what they are, how you choose them. And here are the real ones where we don't even know that this is a coalgebra, Lie coalgebra, this is a Lie algebra. We don't know. We have to see them as vector spaces down at the level of the real ones. So let me just give you the key word about the motivic ones, which is, when you get down to here, you have a great advantage, which is that you know all the relations satisfied by your symbols. But when you get down to here, you don't know that anymore. You lose that advantage. Let me take the bar off. I want zeta 2. I want the whole general. So who is this then? Of course, you have a whole theory of motives, and you define them, and you know all of this, and you know that motivic multizetas satisfy shuffle and stuffle, so this really is a quotient. But who are they? And so the definition that I'm going to use here today is MZ equals the maximal, this is the real zetas, okay? MZ equals maximal quotient of FMZ that surjects to Z and, here's the key point, the coaction remains a coaction. So if I were to write bars on everybody, which I do like to do sometimes, often, because I just prefer Hopf algebras, okay? This has to be a Hopf algebra. The coproduct has to descend and make this into a Hopf algebra. And that is what we don't know happens down here. We do not know that this one is a Hopf algebra. Okay, so just the maximal quotient that stays a Hopf algebra. And this is a property of the motivic multizetas that can serve as a definition. Ulf doesn't look happy, but I like this definition. Anyway, this is the level that I'm going to stay on today, because this is the one where we know that something is free with one generator in each odd rank. So that's what I'm going to talk about now. Who is free with one generator in each odd rank thanks to Brown's theorem? It's this. So what is this? We forget the formals now. I just explained who they are so that we have an idea of how to define MZs. Now we can forget them. These are multizeta values with zeta of 2, motivic. These are mod zeta of 2. And these are mod, so that's a Hopf algebra by definition, well, or by consequence of the definition. And that's a Lie coalgebra. And so its dual is a Lie algebra. And this is the Lie algebra for which Brown proved that there's one generator in each odd rank, and it's free. Okay, but this Lie algebra is contained just in the algebra of polynomials. And so I want to tell you how to choose polynomials for each generator in a canonical way, pretty much using this diagram. And that's the goal of the talk, really. I have to say, okay. All right, let's do it. And looking at the time. Okay, good. Halfway, that's perfect. Okay, so we have a very simple, there are two ways to do this. One using the Drinfeld associator and one not. So but they're equivalent. So I'll use the Drinfeld associator first. So this, I said part 2 of my talk was duality, and this is it, essentially. Here's the key remark. The key remark that's so simple is that because we have an obvious isomorphism Z here that just takes a word W to Z of W, everything, all of the pairs, the dual pairs are canonically isomorphic all the way down. So let me give you the answer to the question how to choose canonical generators in one line, but then I'll show how to really compute it. This is an isomorphism, so just take zeta of n. Just take the pre-image of zeta of n. That's what they are. So basically, this is about as canonical as you can get. Okay, I will show you how to compute them explicitly, and I will show you something else which has to do with what happens when you return zeta of 2 and you get canonical generators of this one, actually. Also for even weights and not only for odd weights. Okay, so here's how it works. So I'm on to part 3 now, which is the construction of these canonical generators. So first, canonical decomposition of MZ. Okay, so what I'm going to do is MZ, unlike the real zetas, which are a Q algebra, we don't know it's a Hopf algebra, and we don't know it's graded. And if we did know it was graded, everybody would be transcendental, and life would be great, because every minimal polynomial of a multizeta would have different weights, and they would add up to 0. So that couldn't happen if it were graded. So then everything would have to be transcendental. So saying that this is graded and real multi-zeta values we don't know is a huge, huge difference, which is why we never look at real zeta values. Only transcendental number theorists do. But this one is graded. So I'm going to actually give a canonical decomposition of each graded piece. And I'm going to do it this way. Q of the single zeta, and this is true for odd or even n. For even n, the single zeta even is reducible as a product of zeta of 2s, but I don't care. I'm still going to set this is a subspace. And then there's going to be 2 subspaces. Okay, now this one is very easy. It's canonical. It's very easy to say who it is. It's simply reducible MZVs, which means I can construct this space recursively starting with small n. I take all the MZVs in this space for small n and multiply them together in such a way that I get something of weight n, and those things generate this. It's just product of smaller ones. All products of smaller irreducibles. Let's be clear. Product of smaller irreducibles. So it's just the ones that can be obtained as sums of products. Okay, it's just the reducible ones. It's completely canonical. So this is canonical and that's canonical, but one might easily say, yeah, but what about this? There's so many ways of choosing a space of irreducibles. There's so many possibilities. So here's what you do to get this. You take the Z map. I call this the Z map. The Z map. I call it the Z map on every level, all of the time. So you take this. It's sitting inside here. It's sitting inside here. It's a subspace. and you go over here by the z map. And that is your IN. So you can take this, just the n, the weight n part. You could add an n everywhere on this entire diagram to put everything into weight n, degree n polynomials, degree n monomials. The whole thing can be just all done in each graded weight separately. So let's say we're in weight n. So this is, what is it? It's just these degree n polynomials, Lie polynomials. Put them here. And what you really do when you do that, what you do, you take a polynomial. I'll give you one. I'll give you the first one. The first generator, G3, of the canonical motivic zeta Lie algebra, it's given by bracket x, bracket xy, minus or plus, maybe, I hope. One of them is in GRT and the other one is in MZ. So, okay. So I write it down this way. And then, how do I compute the z map? I just put a z, literally, in front of every word. Z of this, it's zeta of 2. Z of this, I have to regularize it. Regularize after this one is zeta of 2, 1. And the others are regularized by the regularization formula. And it just gives me this linear combination of multiple zeta values. And that is how I go from here to here. In this perfectly simple way, just using regularization. So because these spaces are isomorphic, I can figure out which element here is the unique element that lands on zeta of n. And that's the one I'm going to take. Okay, but what I wanted to say before even doing that is, who's this? It's just, all it is eraser lost. Where did I put it? Well, okay, got another one. IN is going to be equal to the Z image of MZV viewed as being contained inside MZV. So I'm taking a subspace of this, I'm applying the Z map to it, and it's going to go into well, I can put n's everywhere, and it's going to go into here. Because Z always goes from a space over to its dual. Okay, and of course, who are these? These are the elements that survive mod products. That these are the elements of the dual here. What does it do? It kills the kernel of the map from here, from here to here. It kills the kernel. The kernel is reducibles, it's products. So this is the map that kills the reducibles. So of course, when I take this IN and I go mod reducibles, it remains an isomorphism on this space. So this really is a supplementary space of irreducibles. And it's canonical. It just comes from the duality, just from taking this on the other side and the fact that it's a subspace. So this is my canonical decomposition. And now that I have my canonical decomposition, here's what I do to calculate all those GIs. Again, there are different methods. Okay, let me use, you all know what the Drinfeld associator is, but I'm going to lift the Drinfeld associator to here. A space and its dual, and I'm simply going to write, so I'm going to put a hat on it, okay? The sum over all monomials of the monomial times z of the monomial. So these are dual bases. Anytime you have two vector spaces, V dual, anytime you have two vector spaces, and you have a basis of one and you pick the dual basis of the other, you can write such an element, call it, it's a canonical element. Okay, now here's a little trick. If you now take a quotient of this space, which is what I'm about to do, and it corresponds to a subspace of this one, this element will descend to the canonical element of that, which means that whatever, now I'm going to, down here, I'm going to call it the sum over W times zeta motivic of W. Okay, now what this means to say that it descends to the canonical element is this. Whatever basis I choose, if I write this element in that basis, whatever basis I choose for this, I write this element in that basis, so I write all the zetas in terms of the chosen basis. The polynomial in front of it will form the polynomials in front of the basis elements will form a dual basis. Okay, so or the same if I choose a basis of this, the same. If I choose a dual basis and I write this element in the dual basis, here I will get dual elements, okay? So I will choose a basis of one side, I will choose a basis of the multizeta side, and I will choose any basis I want, but that has to be compatible with this decomposition. So this has to be in my basis, and then I will just choose a basis of this and a basis of that. The basis of this, in motivic zeta, multizetas, it is nothing but given by all products of lower degree irreducibles that end up of the right weight. They are linearly independent, they're algebraically independent. This is really just the Milnor-Moore theorem. So I have an absolutely canonical, not only the subspace, but its basis is absolutely canonical, insofar as these are canonical. Okay, are these canonical? Do I have a canonical basis for this? This subspace is canonical. Basis? You can, this is free. This is free with one generator in each odd rank. So there's a lot of nice bases you can choose, like the Linden basis. It isn't canonical. People don't call it canonical. Let's call it semi-canonical. Fine, take a Linden basis of this. Take these of the basis elements. And you will get a basis of this, which I won't call canonical, but which is close. It's a nice, good basis. Multiply all those together in every possible way, and that will give you a basis of this, and you just do this recursively all the way up. So now you have a basis of this base. Completely well-defined basis coming from small n and moving up. For small n, there is none of this, and okay. And so you got to have a completely clear basis, so let's use that basis. Okay? And I will write this canonical element, which is the Drinfeld motivic Drinfeld associator, in that basis. And what happens is, I'll write it as phi of n, so of the graded n pieces, okay? And phi of n is going to have a certain polynomial here in front of this basis element plus a sum of basis of r times some hi's and a sum of basis of in times some h, I, j, k, ki's. Okay, it will look like this. Okay, now what happens if I change my basis? I will change my basis as much as I like, but respecting always this decomposition. So this will never be touched, because when I change my basis respecting the decomposition, I only change this part. So I can make all these into linear combinations, and all of these polynomials can change, but I don't care. This one will never change. This one is canonical. So one way to calculate the g's is using the Drinfeld associator. So there's I think I don't have much time left, so. Oh yeah, oh great, perfect. Okay, proposition. So this is what I wanted to tell you, how to get the odd, for odd n, how to get the specific GIs, which are a good set of canonical generators for the motivic multizeta Lie algebra. And they can be characterized in a different way without talking about the Drinfeld associator, which is this way. For odd n greater than or equal to 3, Gn, so Gn, it lives inside here. But that lives inside here. So is characterized uniquely by so if I consider it as living in here, the Z map is going to end up in MZ, and I'm just going to say zeta n if you consider that it's here. And if you consider that it's up here, okay, here there's going to be maybe to go from here to here, you mod out by the reducible. So here, when you do this, you may get something reducible. But there's no irreducible part. This is the key point. So why did I write Q here? Why did I write a little scalar multiple? Just a choice of normalization. I could actually put A equals 1 and have this as my choice of normalization. We found it for our calculations more convenient to also ask this. This is just a choice of normalization, and it makes it that here you have a certain scalar multiple that appears. This is purely a choice of normalization. Of course, Gn is of depth 1. It has to be of depth 1, and therefore it always does have this monomial non-zero. Okay, it's these are the depth 1, the depth 1 generators of MZ, the only depth 1 elements. None of these elements can ever be of depth 1 because they're brackets of depth 1 elements. Okay, so the last thing I wanted to say, this basically answers the question which had to get canonical generators for the motivic multizeta Lie algebra. And the very last thing I want to say is what happens for even values of n and why also the GNs, because you can do this for odd or even n, and you get some even GNs too. And what are they? What do they mean? So my last thing is going to just answer that final question. And for that, I have to go back to this whole idea that this space is a Hopf algebra co-module. So again, the way I like to explain what this structure really means is by doing the dual. I find that wandering around between spaces and their duals is very revealing. There are many things that, like in this case, the irreducibles are good on one side and the reducibles are good on the other side. So it's really good to move back and forth. MZ, so what is this? This is a Hopf algebra module. So as vector space, Francis shows that this one is really just the polynomials in the motivic zeta 2. Polynomial, just tensor MZ bar, tensor the thing mod zeta 2. And so this is going to be the same, okay? Well, it isn't going to be the same. It's going to be the dual. So what is the dual? What is this module? So to say what this module is, let me say, what is it? What is it? What is its description? Okay, so first remark, this one is a Hopf algebra. Now, here we saw it contains this Lie algebra. This Lie algebra is equipped with the Ihara bracket that Ulf talked about in his talk. So this is a Lie algebra equipped with the Ihara bracket. So we have a Poincaré-Birkhoff-Witt theorem that says that then there's a multiplication on this. What is that multiplication? This is a post-Lie algebra. We suddenly find that we are in the world of post-Lie algebra, so Ulf can wake up for a moment. Post-Lie. As he convinced me. After I'd worked with this for innumerable years, one day Ulf came along and said, you know that's a post-Lie algebra. And then I read the paper, and yes, it is a post-Lie algebra. Okay, anyway, that little triangle thing, the action of f on g is df of g. So here I can just take f and g, any element, any Lie polynomials. These are all Lie polynomials, but this can be defined for any Lie polynomials. df of x equals 0, df of y equals yf. That's the Ihara derivation that goes with the Ihara bracket. That's the triangle of the post-Lie algebra. So what that means is that although it's a bit complicated to define the multiplication here, it has to be done the way Ulf was doing it in his talk. But it is easy to define the multiplication f star g if g is in MZ, but f can be anyone. So the complicated rule for the multiplication on this, it becomes a simple rule when the one that acts is in the Lie algebra. Okay, so it's a complicated rule that generalizes this rule basically. It's like half of the Hammer bracket. Okay, so I have a Hopf algebra, and so this, which is what I want, and now I'm just going to write the structure of the Hopf algebra module, which is dual to the co-module. So it's going to be a tensor with this Hopf algebra of something that has to reflect the duality of that. And what that is going to be is G2, G4, G6. So as vector spaces, it has to be isomorphic. So this is a vector space. It has to be isomorphic to that. But you cannot multiply these things together. You cannot use that post. It's not a Hopf algebra. You can't multiply them together. But you do have an action of this on that because it's a Hopf algebra module. So this acts on that. So this acts on that by the same rule right here. The rule for f in mz hat acting on one of these g2i is just f star g2i. So every element of this object can be written as an element of this acting on an element of that with this action here, this exact action. Okay, so this is something that is familiar, very familiar to the people who work on this side. As you always say, you have a power of the motivic zeta 2, and then you have a zeta, and you decompose into two pieces, and this kind of decomposition is very familiar on this side. All even numbers. I'm explaining. Yes, that's right, but they're polynomials. The GIs are just when I had written the Drinfeld associator in weight n, zeta n gn plus the parts with Rn and In. For even n, this is reflecting only the zeta, the even zeta part, the zeta 2. This is the dual of this. They're just a vector space. You can't multiply them. This one is just, yeah, okay, notation. Notation is bad. You're right. Yeah, no, you cannot multiply them. Just vector space. What is the right notation for vector space? Right. Cute. Yes, vector space only. You can add them, but you cannot multiply them. But you can multiply. An element of this acts on an element of that by the multiplication rule. Okay, and these, until the same little reasoning that I gave for the AGNs, these were not canonical either. This structure, I mean, this is the structure that's the dual of that structure. But who to choose for these elements? So, okay, it's a little free bonus for the method that gave what I really wanted, which was generators for the motivic Lie algebra. The free bonus is that you also get canonical generators also, and so the action becomes canonical on the even ones. And that's basically the content that I wanted to tell you today.
Thank you.